The real plot. Are you following along okay with this? A lot of stuff. Here's the mechanism that's been proposed. And so what this is this is the acid chloride of acetic acid. In what's that guy? Here's my magnesium bromide, or my Grignard reagent. This carbon, that's here. The apparent electrons from the double bond are out here as they did before, and I get this intermediate. It's the magnesium bromide salt of this oxygen anion here. Now, what this thing is going to do now is rearrange, where a pair of electrons from here goes back and reforms the double bond. Chloride comes off. Would chloride be a good leaving group? Remember, good leaving groups are weak bases and stable in solution. It's a weak base and a stable solution. Bromide's even better, iodine's better still. Okay, so the chloride comes off, and notice that the carbon I brought in from my Grignard reagent is now attached. The CH3 that was already there is still there, but now I've got the ketone. This is what we were talking about before.
Just another method to form a tertiary alcohol besides having a...
Right, now this if we stopped here, we'd have a ketone. But if I react this with another mole of Grignard reagent, then it's going to behave like an ordinary ketone and give us a tertiary alcohol. With the R group from the Grignard reagent, how we get added twice. Is it making sense? And that's what we're showing here. The Grignard reagent now, the second equivalent of the Grignard reagent, attacks that carbon, the pair of electrons goes out here to form a negative charge. The magnesium was part of the Grignard reagent, ends up out here as an ion pair, a salt. Then, when I treat this with aqueous acid, it's not showing the acid, the aqueous acid produces the alcohol. And two R groups from the Grignard have been added to the carbonyl carbon. Could we draw the same thing with an ester? We have the courage to do the same thing with an ester, we do the same thing. Should we do it? Let's do it. You can prompt me.
All right, bring it on.
Good luck.
Let's do this.
Thanks for that, Paul.
John will correct us.
All right, let's do again acetic acid. OCH3. And here's my Grignard group. Let's bring in RMGBR. What's going to happen here? Yeah, this guy's going to act like it's carbanion, and it's going to attack here. True? And I've drawn this in a slightly different orientation than what we saw before, but that's going to give me R, and a pair of electrons by the way. We'll block here as that attacks, and we'll get CCH3, OCH3, O, single bond. Now all three pairs are out here. We've got a negative charge. Sitting there with that is the magnesium bromide. It's positive charge. So far, so good.
And we know it attacks that carbon because it's the delta.
Say that again.
It's the delta positive on that carbon, right? That's why it attacks that. Okay. Just so I can think through it on the test. I'll be like, why did you attack that?
Because of this carbon.
Okay. All right.
Now what's going to happen, just as it did before, this pair of electrons is going to come in here like this. This pair of electrons is going to go out here like that and make the alkoxide. Okay? So in the next step, oops. Plus, I'm going to have magnesium bromide and then the alkoxide as part of the magnesium bromide side.
Why does it do that?
Well, why it does it is a good question.
Oh.
That's just what it does.
Okay, all right.
There's a lot of things that we can tell, we can cite great detail about what happens. We can't really tell you why.
Let's just remember it.
But remember, over here with the acid chloride coming off, that was actually the previous slide, the chloride ended up with the magnesium and the bromine. We had magnesium bromide chloride. Here it's the alkoxide that becomes part of the side. Okay, and we get a ketone, and then this would react in traditional fashion. When another one of these guys here, we get the salt again, hydrolyzed with acid, we get a tertiary alcohol. If you like, repeat that twice. It's really the same mechanism. Only difference is this comes off instead of the chloride.
So that's your ketone, you add the acid to the chlorine.
Yeah.
Tertiary.
Well, we need to do one more Grignard reaction. This guy attacks here again. That goes back out there. And we react. CH3. Oops.
So there's really no reason why it takes the methoxide instead of just that?
The best leading group will leave.
Okay.
Oh,
And
okay.
the alkoxide is a better leading group than the methox, or methide.
Okay.
In fact, we pretty much can't create methide ions, they're such powerful bases. And this is a pretty powerful base also, but it's the best leading group that we have left. So, anyway, we've got this. And using bromide here, and then we treat that with acid, and then we get that. Oh, plus it's 3 sorry. Slock and I have much work over here, much more work. Are you okay with the ultimate consequences here? If I treat with a stoichiometric double amount of Grignard reagent, either acid or chloride, I'm going to get a tertiary alcohol. Where the carbonyl now has 2 of those Grignard carbon groups attached, and the alcohol is tertiary. Now, here's one of the unusual reactions I was talking about a moment ago. Remember when we talked about making epoxides? Ethylene oxide is an epoxide. How do I make ethylene oxide, by the way?
Would you make it?
I would take ethene and react it with what?
Some sort of a oxidizing agent, like a...
A peroxy acid, like metachloroperoxybenzoic acid, like we were talking about earlier. And that gives me the epoxide. Okay, this 3-membered ring is an epoxide. And I could make that by taking ethylene and reacting with peroxy acid. That is very reactive. These carbons are electropositive, and now my Grignard reagent sees those carbons and attacks here. This releases a pair of electrons to oxygen, and I get this intermediate, which when treated with acid gives me a primary alcohol. But now, as opposed to with formaldehyde, I've added 2 carbons. So this is a way to add 2 carbons to the R group, Grignard R group, and make a primary alcohol. If I have formaldehyde, I get 1 carbon added. This gives me 2. All epoxides will do this as well, given all possible combinations. Now this one's handy because it's very clear what's going to happen. But could I use a propylene oxide, which is based on propylene and an epoxide? The answer is that.
So is it going to be...
Generally, if I have a more complex epoxide here, the Grignard reagent will attack the least crowded carbon. Creating the alcohol.
The least crowded alcohol?
The least crowded carbon. So if one of them's just got 2 hydrogens on it, one of them's got a methyl on it, like propylene oxide, it would attack the least crowded carbon. Just for steric or crowded conditions.
Is it like an anti-Markovnikov, or is that like?
What's that?
Is it like an, so is it anti?
Yeah.
Markovnikov thing?
Yes. Here's my Grignard reagent. And here, let's do propylene oxide. I got too many. Now, which of these carbons is more crowded?
It's methyl.
This guy. So this guy is going to attack here, the ring will open up so that the alcohol is here. Does that make sense? When you're doing Grignard reactions, the Grignard reagent will attack the least crowded carbon. In this case, I did a secondary alcohol. And again, you need to pick, you need knowing how this reaction occurs, you need to pick and choose appropriately to get the alcohol that you want. All right. We're moving right along. Are you doing okay? I know it's a lot of stuff. You were talking about this previously. Grignard's a good nucleophile, but they're also good bases. So we can't use solvents that contain OH, NH, SH, or even terminal alkynes. You probably don't. What's the deal about terminal alkynes? Yeah, more acidic than we would expect. The hydrogen on a carbon triple bonded on the end is acidic enough to react with Grignard reagents. And remember, the Grignard reagent will actually take these acidic hydrogens and just turn the Grignard reagent into a hydrocarbon. And it's lost under its utility. So, we can't work with solvents that contain these guys. We can't work with solvents that contain these guys because the Grignard reagent will attack here, just like it does carbonyl carbon. Okay, so the kinds of solvents that we can use in a Grignard reaction, pretty limited. The ether, the diethyl ether is the one. How do you do it? Okay, is this making sense? We haven't seen it yet. We'll see it later on. But when I do a Grignard reaction, let's say we've got a Grignard reagent like that. What the diethyl ether does is this. This is diethyl ether. And we'll have another one down here. Magnesium is a transition, it's a metal in period 2, and it will form complexes. And the ether molecule is not, there's no acid there, but the ether molecule stabilizes by forming complexes with the magnesium. It stabilizes the Grignard reagent. This is the reason we need the ether there. It's not only a good solvent, but it stabilizes the formation of Grignard reagent. I think we'll see this at the end of chapter 4. That's what goes on. You remember, have you ever seen complexes?
The mangan, or no, that one, that 8 number one you showed us?
Yeah, there's a whole bunch of them. A real couple in biology is a complex that forms with iron in hemoglobin. We've got a bunch of nitrogens in the ring structure, and the non-bonded pairs of the nitrogens are attracted by iron complex. Same kind of thing happens here with magnesium in chlorophyll. The chlorophyll, what we call chlorophyll, has magnesium at its center with a bunch of nitrogens complexing it, and it's important component of the chlorophyll structure. So this is not novel, and the ether structures here stabilize this magnesium form.